So, um, if I asked you to measure the coastline of Britain, you would probably just assume there's, you know, a single correct, mathematically precise answer.
Right, like you just take a map and trace the edge.
Exactly. You trace it, you get a number, and you're done. But what if I told you that the closer you look at that coastline, the longer it actually gets?
Which is such a wild concept to wrap your head around.
It really is. Because, I mean, if you measure it with a 100-mile ruler, you get one number. But if you use like a 1-foot ruler, suddenly you're measuring every little inlet and every rocky peninsula.
And the length just skyrockets.
Right. And if you measure around every single grain of sand, the coastline of Britain literally approaches infinity.
Yeah, it's a mathematical paradox that completely breaks our traditional understanding of geometry.
It really does.
Yeah.
Welcome to your deep dive. We've tailored today's exploration specifically for you, working from a really comprehensive stack of source material.
A lot of great sources today.
Yeah, detailing the life, the theories, and the profound legacy of Benoit Mandelbrot. He was this Polish-born French-American mathematician who basically looked at the infinitely complex, jagged, chaotic parts of nature that everyone else was just ignoring.
And, he found this breathtaking hidden order in all of it.
Exactly. So for centuries, if a shape wasn't perfectly smooth, like a flawless sphere or a straight line, traditional mathematics essentially just threw its hands up.
They did. I mean, the academic establishment literally viewed the jagged, messy realities of nature as monsters. That was the term.
Wait, really? Monsters?
Yeah, they were seen as these unnatural curiosities that just didn't belong in serious science. But, Mandelbrot proudly referred to himself as a scientific maverick.
Which is such a great title.
Yeah.
And our mission today is to give you a completely new lens through which to view the physical world.
We're going to look at the exact mechanics of how he proved that the messiness of reality isn't some error. It's a fundamental design.
Right. And to understand how he was able to see the world so differently from all those rigid academics of his time, we kind of have to look at how he was educated, or, well, how he wasn't.
Yeah, his childhood completely bypassed that traditional smooth path of rote memorization.
So, okay, let's unpack this. He was born in Warsaw in 1924.
Correct. To a Lithuanian Jewish family. His mother was a dental surgeon and his father traded clothes. But the real influence on his intellectual development was actually his uncle.
Right, because his uncle basically despised traditional schooling, didn't he?
Totally. He completely took over young Benoit's education. So instead of having him sit at a desk reciting, multiplication tables all day, his uncle taught him by playing chess.
Oh, wow.
Yeah, and by having him read complex maps and just actively demanding that he observe the physical world around him.
Which feels incredibly significant when you look at his later work. It's like his uncle was giving him a mental sandbox instead of a strict curriculum.
That's a great way to put it.
Right, because by reading maps instead of equations, he was basically training his visual intuition.
Yeah.
He was learning how to navigate real-world topology instead of memorizing abstract formulas.
Exactly. He was building this foundation of geometry based purely on sight and physical reality, which, he really needed because his physical reality was about to completely shatter.
Right, 1936.
Yeah, the threat of Nazi Germany was rising, and his family fled to France.
They were running for their lives. And, I mean, the source material details this horrifying reality. While they survived the Nazi occupation, they were living in just constant, agonizing fear.
Constantly hiding from authorities.
Terrified of being denounced by their own neighbors. And Mandelbrot later recalled how a close family friend, a physician named Zina Morhange, was actually turned into the Gestapo.
By a rival doctor, right?
Yes, simply to eliminate the local medical competition, which is just, it's sickening. But it makes you wonder, how that specific trauma, that constant displacement, shapes a young mind.
Oh, absolutely.
Like, did this constant displacement and survival mindset actually prime him to question the rigid rules of traditional academia later on? I mean, if you spend your formative years dodging the Gestapo, the neat, orderly rules of a textbook probably seem like a complete lie.
What's fascinating here is that is the critical insight into his psychology. I mean, the academic establishment of the 1940s and 50s, they loved order.
They wanted everything in predictable boxes.
Exactly. But Mandelbrot knew from personal experience that life is fundamentally unpredictable. Because his early life was so chaotic, he didn't view chaos as an enemy to be defeated by math.
He viewed it as the baseline.
Yes. He was uniquely equipped to look at chaotic systems and actually try to understand them on their own terms.
But, having a unique perspective is one thing. Actually, proving it to the academic world is another.
Oh, for sure.
So after the war, he earns a master's in aeronautics at Caltech. He gets his PhD in Paris. And then in 1958, he lands at IBM.
Where he ends up spending 35 years.
Right. But here is what I don't get. He has these radical ideas about infinite jagged complexity in the late 1950s and 60s. How is he actually visualizing these mathematical monsters before modern graphic screens even existed?
Well, he had a tool that almost no other pure mathematician at the time possessed.
Right.
Access to IBM's mainframes.
Oh, right.
Yeah, these were massive room-sized computers, literally the most powerful calculating machines on the planet. And Mandelbrot wasn't necessarily some brilliant programmer himself, but he realized these machines could act as telescopes for mathematics.
A telescope for math.
I love that.
Yeah, he took earlier, highly theoretical work by French mathematicians, like Gaston Julia, for instance.
Right, the Julia sets.
Exactly. Equations that basically involved feeding a number into a formula, getting a result, and feeding that result back into the formula in this infinite loop.
Which is just impossible to do by hand if you want to actually see the shape it makes. I mean, you'd be doing arithmetic for 1,000 years. Precisely. But the IBM mainframes could run those feedback loops millions of times overnight and then just print out the results. So for the first time in human history, Mandelbrot could actually see the shape of these infinite equations.
And then in 1975, he finally gives this new geometry a name. He coins the word fractal.
From the Latin word fractus.
Meaning broken or shattered glass. Which is just, it's such a poetic description for a man studying the jagged edges of reality.
It really is.
And by 1979 and 1980, using those IBM computers, he finally visualizes the iconic Mandelbrot set.
Right, the Mandelbrot set, that swirling, beautifully complex, endlessly repeating geometric pattern. I mean, if you zoom in on the boundary of the shape, you find miniature, nearly identical versions of the whole shape.
Just going down into infinity.
Yeah, but Mandelbrot was very clear about his role in this. He famously stated that he didn't invent the Mandelbrot set, he discovered it.
The math was already there.
Exactly, hidden in the fabric of the universe.
He captures this perfectly in the intro to his book, The Fractal Geometry of Nature. He writes, clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line.
That sentence was basically a declaration of war against traditional geometry.
Wait, so you're telling me mathematicians basically ignored the shape of a cloud for centuries just because it wasn't a neat little Euclidean sphere?
That's exactly what I'm telling you. They just called them program artifacts or anomalies. But Mandelbrot argued that the things academia considered a mess actually possessed a deep fundamental degree of order.
Wow.
He brought unity to knowing and feeling. Like, you can look at a fern leaf and physically feel its repeating pattern, though every tiny branch looks like a miniature version of the whole leaf. Mandelbrot provided the math to actually know why that happens.
And this brings us back to our coastline thought experiment. In his 1967 paper, How Long is the Coast of Britain?, he introduces this concept of self-similarity and fractional dimension.
Which later gets applied directly to fractals, yeah.
Right. But this doesn't just apply to coastlines. Here's where it gets really interesting.
Oh, it applies to almost everything in nature.
It's like zooming in on Google Maps. You zoom into a rugged coastline, and the new, closer image looks exactly as jagged as the zoomed-out one.
Yeah. The computer scientist Stephen Wolfram observed this perfectly. He noted that fractals are equally rough at all scales. A rocky coastline looks just as jagged from a satellite in space as it does when you're standing right on the beach.
For, like, Romanesque broccoli?
Right. The head is made of smaller florets that are perfect miniature copies of the entire head.
So if we connect this to the bigger picture, his theory of roughness basically gave humanity a truthful way to measure the untamed Earth.
It shifted how science models reality entirely. But, he didn't just stop at the Earth. In 1974, he takes fractal geometry and applies it to physical cosmology to solve Olber's paradox.
Now, for those listening who might not know, Olber's paradox is the riddle of the dark night sky. Basically, if the universe is infinite, and it has an infinite number of stars, then no matter where you look in the sky, your line of sight should hit a star.
Right.
So the entire night sky should just be this blindingly bright white. But it isn't. It's mostly dark.
And traditional science leans heavily on the Big Bang theory to explain this. The idea that the universe has a finite age, so the light from infinitely distant stars simply hasn't had enough time to reach us yet.
But Mandelbrot says, wait, what if the structure of the universe itself is a fractal?
Exactly.
So how exactly does that solve the paradox without needing the Big Bang?
He used this mathematical concept called Cantor dust.
Okay.
So imagine taking a solid block of matter and you remove the middle third of it.
Right.
Then you take the remaining pieces and remove the middle third of those. If you repeat that process infinitely, what you're left with is a fractal distribution of dust.
Just tightly packed clusters of matter.
Yes, separated by massive, proportionally larger voids of absolute emptiness. Mandelbrot theorized that stars might be distributed exactly like this.
So instead of stars being spread out evenly like some infinite glowing fog, they're clustered in fractal patterns.
Correct. And because of the mathematically predictable way those massive repeating voids scale up, the light from distant clusters gets trapped and diluted in the infinite emptiness.
That is wild.
He proved mathematically that if the universe is structured as a fractal-like Cantor dust, the night sky would naturally be dark, regardless of whether the Big Bang happened or not.
That is just a staggering application of a single geometric theory. I mean, we're talking about the shape of broccoli on your plate and the distribution of galaxies in deep space.
It's all connected.
But human beings are part of nature too. And Mandelbrot realized that if nature follows these jagged, repeating, chaotic rules, then human-made systems, especially the really chaotic ones, they must follow them as well.
Which brings us to the stock market.
Right. This is where his work gets incredibly pragmatic.
Yeah, he turned his attention to financial markets. Historically, economists modeled market risk using Gaussian distributions.
Which we commonly know as the bell curve.
Exactly. And the core assumption of a Gaussian model is that variations are smooth, they're independent, and they're predictable.
And crucially, under a bell curve, drastic extremes are statistically so rare that they are virtually impossible. Like a massive, catastrophic market crash might be modeled to happen once every 10,000 years.
But Mandelbrot, he just didn't trust the smooth math. He looked at the messy data, so he gathered daily records of cotton prices dating all the way back to the year 1900.
A huge data set.
Huge. And when he charted decades of this actual human trading, he found that the price changes completely rejected the smooth bell curve. Instead, they followed what's known as a Levy-stable distribution.
Okay, let's really break this down because the sources mentioned a specific parameter shift here.
Right.
The standard bell curve operates on a parameter of 2.0. Mandelbrot found that the cotton market operated at a parameter of 1.7. To someone listening, 2.0 to 1.7 just sounds like a slight decimal shift. Why does that completely rewrite the rules of financial risk?
Because that parameter actually dictates the shape of the curve's tail. In a Gaussian curve with a parameter of 2.0, the tails, which represent extreme events, they taper off to zero very, very quickly.
So it assumes extreme events basically just don't happen.
Right. But a Levy-stable distribution with a parameter of 1.7 has what mathematicians call fat tails.
Meaning the probability of a massive sudden swing doesn't drop to zero.
Exactly. It represents infinite variance. And in a system with infinite variance, extreme events decay much, much slower.
Wow.
It proves that the market has long-range dependence and extreme concentration. Mandelbrot literally called this wild randomness.
Wild random.
Yeah. He was proving that catastrophic drops, those sudden jagged cliffs on a stock chart, they are not rare, unpredictable anomalies. They are a fundamental, mathematically baked-in feature of the system.
Nassim Nicholas Taleb, who wrote The Black Swan, famously called Mandelbrot's book The Misbehavior of Markets, the deepest and most realistic finance book ever published.
High praise.
Very high. So what does this all mean?
Let me ask a pointed practical question on behalf of the listener here. If Mandelbrot figured out that the stock market operates on the same wild randomness as a fractal, why aren't all fractal mathematicians billionaires?
That's the big question.
Right.
But you have to understand the difference between modeling risk and predicting the future.
Yeah.
Mandelbrot didn't invent a crystal ball. He couldn't tell you what the price of cotton would be next Tuesday. But he proved that building our global financial systems on the assumption of smooth, predictable variations is a really dangerous, willful illusion.
So he was basically telling them, your models are ignoring the very real probability of ruin.
Yes. A fractal model tells you that a devastating valley is coming eventually, and that the overall shape of those crashes is entirely normal for the system.
So when a hedge fund blows up because of a quote-unquote once-in-a-lifetime anomaly, Mandelbrot's math proves that they were simply using the wrong ruler to measure the risk. They were trying to measure a jagged coastline with a smooth sphere.
Which leads to an incredibly complex legacy. I mean, the source material outlines how he contributed to meteorology, linguistics, medicine, anatomy, economics. He was just everywhere.
He was a true polymath.
But because his work crossed so many strict academic boundaries, the gatekeepers of traditional academia didn't really know what to do with him for a long time.
Yeah, he was a massive late bloomer in terms of traditional academic recognition. Like we said, he operated entirely outside of the standard university track for decades at IBM.
Right.
He actually didn't receive his first tenured academic post until he joined Yale in 1999.
And he was, what, 75 years old?
75, holding the record as the oldest professor in Yale's history to receive tenure.
That's incredible. But, his influence completely spilled out of the ivory tower anyway.
Mhm.
Pop culture embraced him in ways that pure mathematicians rarely experience.
Oh,
I mean, the indie musician Jonathan Colton wrote a tribute song titled Mandelbrot Set. It literally includes the lyric, "You're one badass thing, Fractal." You just do not see a lot of 75-year-old math professors celebrated in indie rock anthems.
you really don't, but it speaks to how deeply his visual geometry resonated with people outside of mathematics. Anyone could look at a fractal zoom on a computer and just feel the infinite scale of it.
But, when you operate on the very fringes of society for your entire life, traversing academia, the corporate labs of IBM, and then pop culture, you inevitably brush up against the highest echelons of wealth and power.
Yeah, which sometimes includes its darker underbelly.
Exactly. Our sources note a very strange historical footnote regarding his later years. His name actually appears in the Jeffrey Epstein files.
Yeah, the details from the source material are brief but factual. In 2010, Jeffrey Epstein offered $50,000 to purchase Mandelbrot's papers.
Okay.
Mandelbrot ultimately postponed the sale, citing his sharply declining health. He sadly died of pancreatic cancer in October of that year. But the sources confirm a meeting had been scheduled in Cambridge, and they were photographed together at Epstein's home in New York at some point.
It is just a bizarre collision of worlds, but, this raises an important question about what it actually means to be a maverick. Mandelbrot's entire existence was defined by rejecting the safe, smooth center of the establishment.
He survived the horrors of World War II by hiding in the margins. And he revolutionized geometry by looking at the messy edges of nature that everyone else just discarded.
Right. He proved that the most profound discoveries often demand that you exist on the jagged edges of your field.
The academic center was just too obsessed with perfection to see the truth. He took the chaos of reality, the storms, the rugged mountains, the crashing markets, and he showed us the underlying structure. Nature wasn't ignoring the rules of geometry, it just had a much more sophisticated rule book.
Which is such a powerful thought. As we wrap up this deep dive, Mandelbrot's greatest gift to us wasn't just giving dorm rooms a cool psychedelic poster.
No, not at all.
It was the profound realization that the messiness of the world you navigate every single day is not a mistake. It is an intricate, endlessly repeating design.
A design that connects the micro to the macro, tying the shape of a riverbed to the structure of the cosmos.
Exactly. And we want to leave you with one final, unexplored nugget from the source material to ponder today. We briefly mentioned that Mandelbrot contributed to linguistics.
Right, which sounds totally unrelated, but
But it's all fractals.
yeah.
He did this profound work on something called the Zipf-Mandelbrot law. It is a discrete probability distribution that models the frequency of words in human language.
It mathematically describes how a small number of words are used incredibly often, while a vast number of words are used very rarely. And it maps this distribution with just stunning fractal precision.
So consider this as you go about your day. What if the very words you use to speak, the frequency of how you construct your daily sentences, the way you build paragraphs in an email, what if language itself is governed by the exact same fractal geometry as the branches of an oak tree or the rocky coast of Britain? It turns out you don't just live in a fractal world. The very thoughts in your head and the words escaping your lips might be speaking in fractals too.
It's a really humbling reminder of how deeply embedded we are in the natural order.
This really is. So the next time you look around and feel overwhelmed by how chaotic and unpredictable your life or the world seems, just remember Benoit Mandelbrot. The chaos isn't a broken system. You're just zooming in on the beautiful, jagged fractal reality we all share.